Okay?
I'm recording.
Let's go. All right.
What we need is a rocket. We can show the world that space is more than a dream or the realm of faraway astronauts. It's right above our heads, and we have the chance to bring it within reach. So make a rocket. Make it suborbital so we can easily recover our payloads. It will have to be small and reusable so that anyone can put a payload into space. I'm John McCabe. I'm an aerospace engineer, and for several years I've wanted to make a rocket. With improving technology, useful payload sizes have been decreasing, but little has been done to develop dedicated vehicles for smaller, less expensive payloads. The only option has been to bundle them together on commercial satellite launches. This practice imposes a rigid schedule and harsh restrictions on the types of materials and experiments that can be flown. Costs are quite high. I believe there's a cheaper and easier way of getting small payloads into space. A small rocket, dedicated to launching payloads of less than 5 kilograms, would have dramatically lower fabrication and operation costs. This is especially true if the rocket is designed to stay in space for only a few minutes, instead of boosting all the way into orbit. Such a rocket trades extended orbital flight times for lower costs and easy parachute recovery of the payload. Moving from design to reality can be a difficult process, but to validate my design, I needed an actual prototype engine and real performance data. The early testing was alternately boring and exciting. Too often, tests looked like this. Though sometimes they looked like this. Once I worked out the bugs in the control system and the hardware, testing became much more reliable. We even managed to get good thermal data from the tests using an infrared camera. The temperatures measured on the chamber walls and the bell nozzle material verified that the engine can survive the long burns required for launch. In this case, the vortex cooling method actually managed to decrease the chamber temperature during operation. The tests also showed that the engine can be safely and reliably ignited with an external ignition source. There is a diverse market for this type of launch service. The initial customers will be enthusiasts like you and me who want to launch things into space just for fun. It will extend to educators seeking to spark scientific curiosity in their students. Class projects could be sent into space and returned for analysis. Finally, there are researchers at universities and in the commercial sector who are trying to test prototypes or study the effects of microgravity and conditions in near space. A small and simple rocket that can get our payloads into space needs the right propellants. In order to avoid expensive turbopumps and separate pressurization tanks, I wanted to use self-pressurizing propellants. This type of propellant builds its own pressure by boiling at ambient temperature. When liquid is let out of the tank and pressure drops, gas escapes from the liquid until it gets back up to the vapor pressure. Nitrous oxide was an obvious choice because it is dense and has a high vapor pressure. Ideally, the nitrous should be paired with a similar self-pressurizing fuel, but there aren't any that are dense enough to keep tank sizes small. After experimenting with several different fuel formulations, I developed a new fuel with all the right characteristics. It can be formulated to pressurize to any desired pressure while maintaining a high density. I work for a small aerospace company in Wisconsin called Orbitech, so I have some experience with rocket engines. Borrowing heavily from previous projects, I came up with a simple and robust design. It uses Orbitech's cold wall vortex technology to cool the chamber walls. This eliminates the complex and expensive cooling channels needed by conventional rockets. By keeping the combustion gases away from the walls, it allows the use of lighter weight chamber materials and improves the lifespan of the engine. The theme of simple and reusable hardware spread to the rest of the rocket design. It primarily consists of 2 big tanks with 4 carbon fiber struts holding everything together. From tip to tail, the rocket will be about 19 feet long and weigh 172 kilograms. Putting together a computer model of the tanks and support structure produced the first version of the Near-Earth Rocket 1, NE-1 for short. The purpose of the NE-1 rocket is to give anyone access to space. Before there is a launch, or anything else, there needs to be a rocket. The NE-1 needs your help. With your donations, we can build it. It will carry your payload of messages or personal items into space. For a few minutes, they will bask in the cosmic glory of the heavens, and then gently float back down to you.